Welcome, and the subject of my presentation is the evaluation of selected machine learning algorithms in acoustic-based road traffic monitoring system. We're looking at two areas in road traffic analysis. Acoustics and road traffic, that's nothing unusual. We normally hear vehicles passing by. We hear the parameters of their driving depending on the engine they have, depending on the velocity, depending on the tires, and depending on the road surface. When the velocities are above 30 kilometers an hour, we talk about rolling noise and the interaction between the road surface and the wheel, the tire of the vehicle. This is a certain issue with electric cars. There are some guidelines in the EU because of them being too quiet. There are some warning signs that they will be generating anyway. For years to come, we will be hearing vehicles traveling. The noise giving us the information about where they come from, where they're going to, and at what speed, and also how they interact with the road surface. The first road detector was built in the 1920s. It would detect vehicles that would approach traffic lights. It was a technologically simple device that didn't last very long. And now MEMS microphones make us come back to the acoustic methodology. Right now they're used in India a lot as pilot projects, but also in Europe, especially in traffic supervision in tunnels, where signs that signal that a package was lost or that there was a collision can be very important. In the case of the selected algorithm, we've chosen 5. Since we analyzed a multi-class phenomenon, we designed the set of algorithms to be able to analyze. So we have the perceptron learning algorithm, we have naive bias classification, regression analysis, linear discrimination analysis, Fisher linear discriminant. All of them were used to analyze multi-class systems. In terms of methodology, the database for the passages, for each of those vehicles passing was done on the roads in the tri-cities, mainly for dual carriageways where there's increased speed, also for a variety of weather conditions. In terms of vehicle class, we did not have even numbers of classes, but such is the nature of natural road traffic. The data was processed by accompanying the sound with the video recording, so we could at all times check what sort of vehicle it was and what was the road surface condition. Then we established parameters. There was a vector of 67 parameters for the sounds that was recorded. Time, frequency, statistical descriptors, changes over time, all this based on the sound of the recording. The vector of the features, depending on the selected method, was chosen. So pre-processing method was devised, so the recordings were clarified in a certain way in order to get the best effectiveness for each algorithm. Then each of the algorithms was trained 300 iterations, for 300 times. The training was selected in such a way as to ensure optimization of the algorithms over time. So we make sure that the deviations from algorithms are at a minimum, and otherwise they work perfect. We therefore evaluated this classification system in terms of graphs. I chose those where you can see the clearest differences. It's probably not surprising that the algorithm that probably took longest to train in terms of F1 score, it was the best. But we came to a conclusion that the algorithm is simply statistically better than all the other algorithms that we tested. In terms of vehicle types, we divided them into 4 categories: light van, heavy, motorcycle, mainly because of their acoustic differences. So we had light vehicles, vans. They're simply slightly larger vehicles. This was dominated by vehicles which usually have a diesel engine, and they can be a little louder, and they're usually also used in SUVs. Then we had heavy vehicles and we had motorcycles. These stood out most from the other classes. It wasn't possible to connect them. You have 1 minute left. Okay, let's move to the second issue. In terms of the road surface condition analysis, we managed to test various types. The most difficult thing was to collect the snow covered because of the climate change. But the evaluation of the road surface condition in the noise measurement indirectly directly or indirectly, directly with laser meters. So we would define the conditions for a given sound by pairing it with the meter from a measurement from the laser. And then we would observe how the characteristics of the sound goes depending on the road conditions. You can clearly see the spectrogram of wet road surface when the droplets go up and down, creating the sound in a high frequency. So again, 300 calculations showed us once again that FLDA was most effective. So this is a matrix of errors and effectiveness. And in conclusion, acoustics gives us a bunch of additional information about road traffic analysis. What we have left is to catch up with technology in order to be able to maintain the microphones in various weather conditions. This is probably the most difficult point, because the ability to take data out of acoustic signals, there's a lot. We can hear things like ambulance sounding, collisions and their characteristics. And of course, the project was co-financed from the National R&D Fund as INZNAK. Thank you very much for your attention.